Welcome back. Welcome back to a course on functions of several variables. In this lecture, we are going to start our new topic, that is chain rule. But before going into it, let us see a problem that is based on the partial derivatives. So we are asked to find out f y x y z if your function of x y z is given as 1 minus 2x y squared z plus x squared y. So this is primarily given. Here we are asked to find out this fourth derivative. So initially what should we do is that we'll have to find del f upon del z. So the outermost is to be found first. So when you find del f upon del z, you may very well see you are going to get this quantity to be 0, and from here you would get minus 2x y squared, and this quantity is again 0. Now let us find this is f z. Okay, now we are about to find f y z, that is del upon del y of del f upon del z. So when you differentiate your minus 2x y squared with respect to y, you would get minus 4xy. Okay, next we are going to fy z, that is del upon del x of fy z. So that is del upon del x. You are operating this partial derivative to minus 4xy, and this gives you minus 4y. And finally your f y x y z is del upon del y of f x y z. So that is del upon del y of minus 4y, which turns to be minus 4. Okay. Then you have something called an increment theorem for functions of two variables. Till now, what we have seen is that we have spoken about the partial derivatives. So only the partial derivative we are talking. So partial derivative means what? If you have a function z is equal to f of xy, you find the rate of change in z whenever there is a change in x, and then you have a rate of change in z whenever there is a change in y. But what happens when change occurs at both the variables? That is, in one variable case, if you have this one, whenever there is a change in the independent variable, what is the change happening in dependent variable? Can we study such kind of an ideology in two variable cases? Yes, of course. That is what is given in this theorem. Okay. Suppose the partial derivatives of these functions are defined throughout an open region R. That is open region R in the sense you have some region. This is considered to be some open region. Open region means, hope you remember, all the points are interior points. Interior points means you must be able to identify some disk which is completely contained in this one. At least one disk has this property. In that sense, we can say this region is an open region. In that open region, we have a point x0, y0, and the partial derivatives with respect to x and y are continuous at the particular point. Then you may write your del z as f of x0 plus del x, comma y0 plus del y minus f of x0 y0. Okay, so as like we have here in the definition of one variable differentiability, we have limit what delta x approaches 0, and this one is f of x plus delta x minus f of x upon delta x, which is written as f prime at x. Okay, so when you try to replace this one delta x minus 0 with some quantity, you will have plus epsilon. This kind of a thing is what you are going to have. The same is written here for two variable setup. Okay, your delta z may be written this way. Okay, so this is an increment theorem for functions of two variables, with which what we are going to do, As your delta x and delta y approaches 0, your quantities epsilon 1 and epsilon 2 goes to 0. So with which we define the differentiability of two functions. I mean two variable function. A function is said to be differentiable at a particular point if the partial derivatives at that point, okay, at the same point x naught y naught, the partial derivatives x with respect to x as well as with respect to y must exist, and your delta z satisfies an equation of this form. Okay, in this case, as your delta x and delta y are very small, your quantities epsilon 1 and epsilon 2 must be very small. In this case, we call f as a differentiable function. Okay, so when do we call a function as differentiable? If it is differentiable at every point in its domain, or we may say the graph is a smooth surface. So in one variable case, it has to be a curve. Here we are saying it has to be a surface. Okay, smooth surface is the thing that we are talking about. Here in one variable case, if you have a sharp edges or something like this, in these cases, we do not have the derivative that exists at a point. So wherever you have a sharp edge, that the derivative does not exist. In this way, they are meaning to say that the smooth curve is the one in which the slope can be found at all the points. Okay, smooth surface means here you may be able to identify your tangent plane at all the points. That is what they mean to say. Okay, so from this definition using the previous theorem, we may very well come to a result that if the partial derivatives of a function are continuous throughout an open region, then the function is differentiable. So in order to verify the differentiability of a function of two variables, first you identify the partial derivatives and check whether they are continuous on R or not. So on R, here R means a region, not the set of real numbers. Okay, you just check it. If it holds true, then you may say your function is differentiable. So of course, if a function is differentiable, then of course it is continuous. But the same result does not hold for the partial derivatives. There we are talking only about this way or that way. Here we are talking in a general sense. Hence, your differentiability will imply continuity. Next, we are about to start our actual content of this lecture, that is chain rule. So what do we mean by a chain rule in one variable setup? Suppose if we are given a function of x and this x, okay, let us take this way. Okay, f is a function of x and x is a function of t. So in this case, what can you find? You can find dy upon dx. This is the thing that you can find, and here dx upon dt you can find. Now, paying attention to these ideologies and look at it very closely, you may very well see that whenever there is a change happening in t, that will affect x. Hence, that will force some changes in x. Whenever a change happens in x, that will force some change in y. So it means a change in t will affect y and induce some change in y. So we are able to identify this one, dy upon dt, and this is nothing but dy upon dx multiplied with dx upon dt. This is the chain rule that we have studied in one variable setup. Coming to the two variable setup, so for functions of two variables, so we have a function z equals f of xy. Here we say your x can be a function of t and your y can be also a function of t. The second one is your x can be a function of t and your y can be some other function of s. And the third one is your x can be a function of both t and s and your y can be a function of both t and s. So with which we may generalize things. Okay, for only for two variables I have spoken now. So the generalization of n variables in any number of variables in z as well as any number of variables in x, that is the dependent variables in independent variables in z, can also be spoken. Now let us pay our attention only to this and see what is happening here. These three are the possibilities. So if this is going to hold, what is going to happen? That is given in this theorem. You may very well see that here instead of z they have taken w to be the function, that is we have w which is a function of both x and y, and this function is given to be differentiable. Okay, and your x is a function of t and y is also a function of t. Then their composite, that is w equals f of x of t comma of y of t. Now this becomes a function of only one variable, which is t. Hence you are able to identify this derivative dw upon dt. But your w cannot be directly differentiated with respect to t. Your w can be differentiated either with x or with y. So that will give you del w upon del x or del w upon del y. Yeah, of course, let it contribute. But your x is a function of t alone. So it is a function of one variable. So you will have dx upon dt plus here dy upon dt. So that is the chain rule in this case. Now let me give you an idea about the second one. Okay, if you look at it, your z becomes a function of x of t and function of s. So instead of x and y, you are going to get some other function of t and s. Right? Only this is going to happen. If this is going to happen, whether you are differentiating with respect to x or you are differentiating with respect to t, it doesn't matter. Okay, initially you had a function of two variables and now also you have a function of two variables. So that doesn't matter much. Fine. So the third one we will see in the later part of this lecture. So now we will see some problems based on this. So the first one is use chain rule to find the derivative of w equals xy with respect to t along the path x is equal to cos t and y is equal to sin t. Also, what is the derivative value at t equals pi by 2? So let us see how shall we do this. So here your w is a function of x and y, your x is a function of t and y is also a function of t. So when you plug this values of x and y into w, you are going to get w is a function of single variable. Hence you can find dw upon dt, which is del w upon del x multiplied with dx upon dt plus del w upon del y multiplied with dy upon dt. Okay, so let us find these values now. From the given information, what is your del W upon del X? It is Y. And del W upon del Y is X. Right? And dx upon dt is minus sin t, dy upon dt is cos t. Therefore, your dw upon dt is y multiplied with minus sin t plus x multiplied with cos t. Now we will have to convert everything to the function involving t. So that is, we'll have to replace the values of y and x. Y is what? Sin t. So sin t multiplied with minus sin t plus cos t multiplied with cos t. So which is sin square minus sin square t plus cos square t. If you make use of your trigonometric identities and solve what it is, yes, of course, that can be done. I leave that to you people. And here we are asked to find out the derivative value at t is equal to pi by 2. That is dw upon dt at t is equal to pi by 2. What this is? This is what we have to find. That is sin squared of pi upon 2 plus cos squared of pi upon 2, which is minus 1 squared plus 0 squared, which is minus 1. Now we will move to our next problem. That is here, if we extend the same ideology to a 3 variable setup, what is the thing that we are going to get? So that is what we are going to see in this lecture. Sorry, in this problem. So we are asked to find out dw upon dt if w is xy plus z and x is given as cos t, y is sin t and z is simply t. Also, what is the derivatives value at t equals 0? Let us get into our solution. So in the solution, here w is a function of 3 variables and x is some function of t and y is some function of t and z is also some function of t. So in this case, if you wish to study what dw upon dt, so first your w can be differentiated with respect to x and your x is a function of t. Similarly, your w is a function of y, so this contributes this term, and then you are going to have a term for z. Okay. From the given information, your del w upon del x is what? Y. Next, del w upon del y is what? X. Del w upon del z is what? 1. And what is your dx upon dt? It is minus sin t. Your dy upon dt is cos t. And your dz upon dt is 1. So when you substitute all these informations into dw upon dt, you may very well see it is y times of minus sin t plus x times of cos t plus 1 times of 1. And when you give the values of x and y into this, you can see minus sin squared t plus cos squared t plus 1. So 1 minus sine square t may be written as cos square t. So it is cos square t plus cos square t, which is 2 cos square dt. If you want to do the simplifications furthermore, yes, of course you can do it. But still here we are asked to find out the value of the function, the value of the derivative when t equals 0. So it is 2 times of cos squared 0, which is 2 times of 1, that again lands as 2. So I have spoken about the third case, right? When your x is a function of two variables, your x is a function of two variables and y is also a function of two variables. In this case, what are you going to get? Okay, that is the thing that we are going to see now. But before seeing those things, here we have we have something called tree diagram in this case. So your w is a function of three variables, namely x, y and z. Okay, these are functions of t. So from this you can obtain here, this gives you actually just a minute. From these things you may have del w upon del z, del w upon del x, del y and del z. And from these things you can find dx upon dt, dy upon dt and dz upon dt. Actually these all are functions of a same variable t. So finally you will land in what? Dw upon dt. That is the main ideology. Okay, now we